P4 we already did. It's, all that fun stuff. Polynomials, multiplying together, FOIL, distributive property, fun stuff like that. P5, though, is a topic you need to know inside and out. Out of all the topics, basic topics I teach in math, factoring is probably one of the more important ones. It crops up everywhere. For every math course, from here until the end, we'll always have factoring in it. You have to factor to solve, factor to do some processes, factor to graph. It's just prevalent in mathematics. So this is one topic you really want to get down pat. So you want to practice it. You want to do actually more homework than I assign on this topic. And you want to know how to do it inside out, upside down, and lying down. Because for P5, it's really nice. They give you one little thing, you factor it, you get an answer, and you're done. When we get to P6, it's going to be factoring 4 or 5 times in one problem to get to the answer. And then later, you just want to be able to factor quickly because that's going to be a small part of the problem, and there's going to be a lot more steps afterwards. So the quicker you can get the factoring done and the more accurate you can get it done, the better you're going to be for the rest of the semester. Okay. That little soapbox. So the first step in all types of factoring. I will ask this many times. What is the first step in factoring? And I'll get several different answers. This is the one I'm looking for. Pull out the GCF. What's GCF stand for? Greatest common factor. The number that is divisible evenly into multiple terms. Now I'm going to show you a step-by-step process, the mental step and all the work, that is used for all GCF factoring. Most people shortcut it, but it's very dangerous to shortcut it because things change in math. You learn it one way, and I twist it around and just throw fractions in it, and all of a sudden you think something else has to happen. This is one of those things that has to happen all the time, no matter what it looks like. So, for example, a simple one. What's nice about this is the exponents on the variables are all whole numbers. It makes things really nice. Do they have to be whole numbers? No, they could be positive or negative. They could be fractions, which even makes it more horrible, and I'll show you one right after this. They could be horrendous. Horrendous, is that a new word? Oh, well, they could be horrendous. But the process that I'm going to show here works for every situation. I could care less what the powers are. So the first thing you do is you tackle the numbers. What number divides evenly into 12, 18, and 24? 6. If you don't know, you could factor tree each one of them and see what common pieces they have. But most people can come up with 6. So we're going to kick out 6. When you're looking at x cubed, x squared, and x to the third, you're going to pick out the one that you could pull out of all of them, which happens to be x squared. X squared is going to be the lowest power of x. So we're going to pull out the x squared. What about the y's? Y to the third is the smallest exponent on them. Now, when the powers become negative, when you say small, you have to lean towards the smallest negative. Like -8 is smaller than -6. So you have to be very careful with negatives. And fractions, that even gets worse because you have to figure out what fraction is bigger than another fraction. All right, when you go back through this problem, this is the mental step. You're going to take the original problem in your head, and you're going to divide out what you factored out. So each one of these is actually being divided by what you pulled out. Again, this is a mental step. So the first term is going to get divided by 6x squared y cubed, and so forth and so on. Now, why does this work? Well, what's cool about this is If you distribute to the first term, what goes away? The bottom and what you factored out, and you're back to the original 12x cubed y squared, or y cubed. So this technique is going to work mathematically. And again, it's usually not so helpful with whole numbers, but when you start getting into fractions and negatives, this is a great technique. So what's left on the outside is 6x squared y cubed, and what's left behind is always left behind with division. 12 divided by 6, x cubed divided by x squared, y cubed divided by y cubed. It's 1, and 1 times 2x is 2x, minus 18 divided by 6, x squared divided by x squared is 1, and 1 times 3 is 3. Y to the 5th over y cubed, y squared. 24 divided by 6, x cubed divided by x squared, and y to the 4th divided by y cubed. If you do this step on paper, you will never ever make a mistake. Ever. Ever, ever. What's the common mistake? Oh, I love things like this. 24xy squared minus 8x squared y plus 4xy. Something really simple. What's the GCF? 4x and a y. So I've seen people do this. Ready? And close the parentheses.
Because it's supposed to be 1.
It's supposed to be 1, but what people think of is they think, oh, it's getting pulled out, so therefore it's not there anymore. But if you think of it this way, it's being divided out, and 4xy divided by 4xy is 1. You have to have the same number of terms on the inside of the parentheses as the same number of terms that you started with. Since you started with 3 terms, inside the parentheses better have 3 terms. That's your checkpoint. All right, so when does this get horrid? Not tricky, horrid. Let's see. How bad can I make this? In calculus,
That's not.
yeah, it's bad enough as it is, you will have a problem that looks something like this. 8x to the 6th power times x minus 2 raised to the negative 2/3 minus 4x squared times x minus 2 raised to the negative 3/2. Still good. Oh, they're fine. The cold keeps them awake. Okay, so here's an ugly problem, but it is done exactly the same as these last two. You're looking for the GCF. What do they have in common? So the easy part, start with the 8 and the 4 and you get 4. The x to the 6 and the x squared? X squared. The x minus 2 raised to the negative 2/3 and the x minus 2 raised to the negative 3/2. All you have to determine is which exponent is smaller. That's it. Which one is smaller, negative 2/3 or negative 3/2? Negative 3/2, because it's further into the negative land. It's further to the left on a number line. So I'm going to factor out x minus 2 raised to the negative 3/2. And this is where my little technique comes in handy. What's left behind is going to be done by division. Let's get this out of the way. 4x squared, x minus 2 raised to the negative 3/2.
You have that first exponent.
Oh, that's supposed to be 6. Yeah. All right, and then I'm going to divide out 4x squared, x minus 2 raised to the negative 3/2. Now the book ones are a little bit neater. This is just the idea. It's not going to come out the way they usually come out. This one's going to come out kind of ugly. All right, so after I divide it out, what's out front is 4x squared, x minus 2 raised to the negative 3/2. With these type problems, I always suggest those brackets to distinguish one piece from the other really quickly. All right, the easy part. 8 divided by 4, 2. X to the 6 divided by x squared, x to the 4th. X minus 2 raised to the negative 2/3 divided by x minus 2 raised to the negative 3/2. What do I do with those exponents? I don't have time to slow down. You subtract them, so you go off to the side. Negative 2/3 minus a negative 3/2. So this is negative 2 plus 3/2. Negative 2/3 plus 3/2. Common denominator is 6, so this is negative 4, 6 plus 6/4. 6. Hold on. Multiply that by 2. Multiply this by 3. This is 9, 6. And negative 4 plus 9 is 5, 6, so that would be 5, 6. So here we're going to get x minus 2 raised to the 5, 6 power. Now the book, of course, that would come out as a whole number, like 2 or 3, but for our purposes, I'm just playing around. Minus. What happens to the 4x squared? That cancels that, just leaves a 1 times x minus 2 raised to what power? Oh, wait a minute. Yeah. Well, it's not going to be power of 1. It's going to be 0, because when you subtract them, you're going to get 0. So this whole piece really is equal to 1. All right, so my final answer is 4x squared, x minus 2 raised to the negative 3/2 times 2x to the 4th times x minus 2 raised to the 5, 6 minus 1. Isn't that pretty? But without this division technique, this problem becomes really, and I mean really hard. But if you show the division, then all you have to do is kind of figure out what's really going on inside of it. So my suggestion, when things get hard, show the division out so you can see what's left behind. It makes things a lot nicer. E5, number 102. I hope there's enough room. 102. Let's see. Negative 8, 4x plus 3, raised to the negative 2, plus 10 times 5x plus 1, times 4x plus 3, raised to the negative 1. This one doesn't have the ugly fractions. But again, it's kind of ugly. Just a little bit. Now, the first thing you have to do is determine how many terms are we dealing with, because that'll tell you how many terms are going to be left behind. So how many terms are in this huge, ugly expression? 2. That's it. There's this big chunk in the front and this huge chunk in the back, but they're separated by 1 plus sign, so there's only 2 terms. So what I'm looking for is a common factor between these 2 terms. So what is the common factor between 8 and 10? 2. And I highly suggest you take out the lead negative sign, so make it negative 2. It just makes things a little bit nicer later on. So pull out a negative 2. What else do they have as a common factor? That chunk 4x plus 3. What power is it going to be raised to? Negative 2. Why would it be negative 2? Because it's further to the left. Negative 2 is further to the left than negative 1. So you pull out the smallest power, in this case negative 2. I warned you about those negatives. You're going to be thinking backwards, and you really need to get in the right direction. What's going to be left behind? Well, I'm not going to show the division, but I'm just going to do it from here. Negative 8 divided by negative 2. That's a positive 4. 4x plus 3 raised to the negative 2 divided by 4x plus 3 raised to the negative 2. Well, they cancel. That gives you 1, and 1 times 4 is 4. Positive 10 divided by negative 2. Negative 5. The 5x plus 1 isn't going anywhere. So he just kind of hangs out. The fun cover.
I got ready to say why. I'm sorry, my mistake.
Well, when you divide out and you have this underneath here, nothing's going to cancel the 5x plus 1, so he kind of just...
Yeah, well, why was, or how come, I can't even ask this question without saying why. Why is 4x plus 3 the greatest common factor? Why is it, because it's smaller?
Oh, the negative 2 one?
No.
Or the 4x plus 3?
Yeah.
It's in both of them.
Oh.
See, there's a 4x plus 3 in the left term, but there's also this 4x plus 3 in the right term. That's a grouped term.
Because they're, okay, I got you.
And then we take out the negative 2 because negative 2 is smaller than negative 1. Yeah. So if u pops down, what's 4x plus 3 raised to the negative 1 divided by 4x plus 3 raised to the negative 2? That's the same thing as asking to simplify this expression. Oops. What's y to the negative 1 divided by y to the negative 2? I'm really worried. You're typing that in the calculator.
Because I don't feel
It's
like
negative
it's
1 minus
plus
a
it's
negative
3.
2.
It's 3.
No, it is not.
Negative 3.
No, it's 1. Negative 1 minus a
I
negative
got my
2
negative.
is the same thing as negative 1 plus 2, and that's why I hate calculators.
Exactly, because I'm totally spoiled on the calculator. I don't even want to count 1 plus 1 without a calculator.
Sad.
It is
Much
sad.
easier to do this.
That's how it is.
So this is left as 4x plus 3 raised to the first power. So what happens is you've taken these negative exponents away from the inside. It's all relatively nice. Now technically, and I'm not going to go this far, you're supposed to multiply this all out and simplify this expression, but it's not really worth our effort. In calculus you have to, but I don't think you'd ever have one that looks that bad. Not in college algebra, yeah, not in college algebra. But that's how it works. It's not that bad. All right.
That's the answer. That's the answer?
Well, remember what I said. If you were really in calculus, you'd have to multiply these two polynomials together, distribute the negative 5. Please don't distribute the negative 5 before you multiply these two polynomials together.
And we got 4 of them.
Yeah, that's FOIL. The distribute is the same thing as FOIL. So FOIL those out, distribute the negative 5, combine the constant term with the constant term. It becomes some ugly expression on the inside.
But we don't have to do that.
But for your purposes, that's fine. That's fine. If you can get it that far, I'd be happy. I'd be dancing. Oh, I wouldn't have to. The point of putting many problems on the test that if you don't get the first one, you're also not going to get the second one. What's the point of putting more than one of these on the test? I always put one type of problem. I don't.
Get back partial credit.
Well, yeah, well, you have to show your work. Yeah, that's why I have you show your work. If you give me an answer, I have two choices. Right? Wrong. Full credit, no credit. I don't think that's fair because a lot of people would have like silly errors. 2 plus 5 is 6. I've had that done. 2 plus 5, 6. Because they're thinking something else. All right. One other thing that we use with GCF is a powerful little tool called factor by grouping. This is still in P5. There's a lot of little pieces in P5 just like there were in P3. Tiny, tiny pieces. So for instance, if you have 4xz minus 2yz plus 6x squared minus 3xy. This technique only works on an even number of terms. Usually for us it'll be 4, but it will work on 6 and 8. A little nastier there, but it will work on them. If this is going to factor, it's going to work out rather nicely. If it's not going to factor, it's not going to work out nicely. The technique is this. Is there any common number all the way across? 4, 2, 6, and 3? No? And then here you have an x, but the second term doesn't have an x. Here you have a z, and the third term doesn't have a z. So there's nothing common between all 4 terms. So what you do is you break it apart. And you look at the first 2, and you look at the second 2. And you treat them as 2 separate problems. And you do GCF to both of them. What's the greatest common factor of the first 2 terms?
2z.
A 2 and a z. And leave things behind with division, and you're going to have 2x minus y. Comment number 1. When you're grouping these things, use the little arrows underneath it. Do not put parentheses to group in this situation. You put parentheses and things get really weird. So just put a little underline to the terms you're going to group together and then factor it out. And after you factor it out, that's when you leave behind parentheses, the distributive property. All right, what's the GCF of the second 2 terms? A positive, you need that operation. 3x. What's left behind? 2x minus y. If this technique is going to work, these two things have to be identical. The group terms have to be identical. 2x minus y and 2x minus y. We're down to two terms. What do they have in common?
2x minus
2x minus y. Left behind?
2z plus 3x.
And you're done. It's a neat technique. Now, there is one little quirk to this problem. If it's set up this way and you factor it out and the two binomials do not match up, do not think that it's unfactorable. Go back to the beginning and take the two middle terms and flip them and try one more time. Because sometimes the order of the two middle terms will determine if it works or doesn't. Now, if you tried it both different ways and neither of them work, then it's probably a prime expression, but I will never give you one of these as prime. So there is that possibility that you might have to take these two terms and switch them.
So you have the option to change the order.
I always have the option to change the order. What property? No.
No, a community.
Commutative. Anytime you change the order, addition, or multiplication, it's commutative. So there is that type of problem where you have to take the two middle terms and switch it. You will find it on your homework. So be really careful. If it doesn't work one way, take those two middle terms and switch them. Try it one more time. See what happens.
Are you bringing the sign over?
Oh yeah, when you flip this, that negative has to be attached to the 2yz. You can't, because you can't flip over subtraction. Don't do that. These things are like puzzle pieces. You have to group them as terms. They take the sign with them. So when you move these around, you have to take them as a puzzle piece. You can't just take a part of the puzzle. You know, cheating on a puzzle is ripping off one of those little tabs that get in your way and then shoving it on. You can't do that in math. All right. So where do we use this factor by grouping? I mean, it comes in handy there, but most problems don't look that way. So it's just a technique for us. If I have x plus a times x plus b, can I multiply them together? Yeah. What do I get out of it? X squared plus bx
Plus AX
plus ax
plus AB.
plus ab, either FOIL or distribution. Okay. Now, usually when you multiply these two types of polynomials together, you can combine the middle terms. Can I combine the middle terms? Why not? Aren't they like terms?
No, well, they have an X in common.
They have something in common, therefore they are like terms. So how do I add like terms together?
Pull out the X.
Pull out the x. So left behind is going to be x squared plus, we're kicking out the x. It doesn't matter which side you kick it out to because it's commutative property. And then we have this plus ab at the end. What's left on the inside of those parentheses?
B plus A.
B plus a, or I can write it as,
A plus B.
it doesn't matter because of commutative property. I just like alphabetical order. Okay, what's neat about this problem is in the middle step it has four terms. And if I group and factor like over here, I'll end up at the beginning. I'll have x plus a times x plus b, or vice versa, x plus b times x plus a. But what's neat about this is, down here, how many terms do you have? 3. You have x squared, you have a plus bx as your second term, and ab is your last term. This is a trinomial. So what this is saying is, now I can take a trinomial, break it up into 4 terms, and factor it. So, for example, if I have x squared minus 5x minus, let's do plus 6. You can't make these up off the top of your head and hope that they factor. They have to be a certain type to actually factor. The way this is going to work is, we have a sum of AB in the middle, and we have a product of AB at the end. Which one is more unique, a sum or a product? Product. Because sums, you know, you can go positively and negatively and always have the difference between the two numbers to be exactly the same. Where products, I mean, this is 1 times 6, 2 times 3. That's it. So the way this is going to work is we're going to look for factors of this last number that'll give us the middle number. Now we've got to be careful. Operations get a little weird here, but we'll start off easy. So this is going to read factors of 6 that add up to a negative 5.
2 times
Factors that add up to negative 5.
negative.
Now, is it 6 and 1?
It's one and negative 6.
It can't be 6 and 1 because to get to 5, you have to subtract. And I said add. So it has to be 2 and 3. So what we're going to do is we're going to split this middle number into a 2 and a 3. But 2 plus 3 is positive 5. And I need it to be an x. So both of them have to have an x, and they both have to be negative. Negative 2x and negative 3x is the same thing as negative 5x. Bring down the first term, bring down the last term. So now we've taken a trinomial and split it up into a 4-term polynomial, quadnomial, and now we can group and factor. What's the GCF of the first 2 terms? X, what's left behind? X minus 2. What's the GCF of the second 2 terms? Careful. You want to take that negative because that usually gets in the way. So kick out a negative 3. Left behind?
X minus 6 minus 2.
Positive 6 divided by negative 3? Negative 2. Then these 2 terms are exactly the same, which is exactly what I want. So I'm going to kick out x minus 2. What's left behind?
X minus 5.
And that is the factor of x squared minus 5x plus 6.
Do you have to do it that way? Yes, because your way will pull out
Well,
mistakes.
Well, hold on. Do you have to do this one this way? No, there's a shortcut. But there's a danger for every shortcut. And what I'm going to do is avoid that danger by doing it this way all the time. Now if you want, you can do this a shortcut way, but I warn you, it gets a little messy later on. There's a problem where if this is what's considered a lead coefficient of 1. If it has a lead coefficient of 1, shortcut works. If it doesn't have a lead coefficient of 1, shortcut does not work anymore. And then people go, oh, and they give up. So what I show you is a way that works for all problems, and if you get stuck, you can always use my method. If you can do a shortcut method and get the right answer, great. I'm happy with that.
But it's just like I got the way I know how to do it in my brain and your way. It's like it's all getting tossed up, and I'm like,
Okay, throw out what's in your brain for a little while, and we'll come back to it later. What I show you is the basics of why it works, and then you can do whatever you want to it. But this method, even as ugly as these problems get, this method will always work. So if you get stuck, this is what you want to come back to. Just like that dividing through by the greatest common factor, it's a technique that always works, and it's used when you get stuck. So I show you the stuck method first, and then you can shortcut. Continue with, what is this, P5, factoring? And we did Gcf factoring, and I did warn you that Gcf factoring is the first thing you should do no matter what's going on. So for instance, where's my notes? Let me steal one. No. That's not it. There we go. We did that. Did we do this one? I think we did this one. Let's try this one. Now, later, about 5 minutes from now, I'm going to teach you how to factor a trinomial with a lead coefficient other than 1, and shortcuts don't work on it. If you try to do this problem like that, it'll mess things up. The first step has to be followed, which is factor the GCF. So do the 3 terms have something in common?
Yeah.
The 3
And a Y.
and a y. You have to pull both of them out. Nice things happen after you pull them out. The numbers get a little bit smaller, and variables that you don't want to work with kind of get pulled away from things. So if you pull out a 3 and a y, what's left behind?
X
Squared minus 2, 10x plus 12.
Remember, you're dividing it out technically, so if you ever get stuck, just sit there and do division. 3x squared y divided by 3y, leave things behind. All right, now we can ignore the 3y and just concentrate on what's on the inside. The pattern that you want to work with now is you concentrate on the last number, 24. You say, well, what are factors of 24? And you really need to say this, that add up to. Because if that's a minus, you're going to say they subtract up to. And we're working with integers, so if they're going to add, what has to be true?
One has to be positive.
Well, two negatives.
They either have to be both negative or both positive. If that was a minus sign, then one's positive and the other one is negative. It gives you some clues. So, factors of 24 with the same sign, it'll give you negative 10.
2 and 12.
Did you just say sex?
No. Negative.
Freudian slip.
-6 and a -4.
Negative 6 and negative 4. So I'm going to separate the negative 10 into these two numbers. They both have to have what attached to them?
X.
An x. And then bring down the 24 and bring down the x squared. What am I ignoring?
Wait a minute.
3y.
What do you mean, wait a minute?
No, maybe I was thinking something else in my head. I thought you would do like x minus 6 in the parentheses.
You're jumping into shortcuts. I don't want to do shortcuts. I'm not doing shortcuts.
Oh, that's a shortcut?
I know, but there's a reason I don't want to go into shortcuts, because I know what's coming next. Something that does not have a shortcut, but you have to do it this pattern.
Oh,
Okay?
okay.
I know I'm being a little weird on this, and I'm like, oh, we already know how to do this. That's great. It's the next one that I'm worried about. I'm not worried about this one. All right, that 3y, just ignore it for a little while. It really is still part of the problem. I don't want to write it here because it kind of gets in the way. All right, group the first two. What can I pull out? X. What's left behind?
X minus.
X minus 6.
What can I pull out of the second two?
Negative
I have to pull out a negative 4. The sign is, I want that first sign to be positive on the inside, so I've got to pull out that negative. So negative 4 left behind.
X.
X minus 6.
It's going to be minus 6 because it's positive 24 divided by negative 4. And then I can kick out x minus 6 because it's a common factor now. It's in both terms. What's left behind after I divide it out? This x and this minus 4. The only thing you have to remember now is that 3y is sitting out front. You got to bring him back into play. So your final answer is 3y times x minus 6 times x minus 4. Woohoo! Isn't that easy?
It's so long.
It's long. Here's the cool thing. You'll never get it wrong.
Let's
It has a checkpoint right here. If these two do not turn out to be exactly the same, you've chosen the wrong numbers. The shortcut, if you just write the answer down, you have no idea unless you check your work if you chose the wrong numbers. Guess what most people do? Choose the wrong numbers.
So we were taught to check, always check.
Yeah, FOIL it out and all that. But that takes actually more time than just doing this.
Right.
So this is a guaranteed way of getting the right answer. Plus, if the problem gets harder, there is no shortcut for the harder one, and it's done exactly the same as this. So if you get used to this pattern, then all of them become exactly the same, and guess how many things you have to learn? Instead of...
Can we do another one like
What
that?
is the name of that problem?
What's what?
What is that called? That problem you said earlier.
Oh, when this is minus?
At the top. What's like the equation? So I can write it down. A trinomial.
Oh, it's just a trinomial.
Trinomial. A factor.
Factoring a trinomial.
Okay.
Can we do another one real quick?
Oh, yeah. I just gotta find it.
Just give it a go.
Here's one.
Yeah, so we can see how you do it your way.
Okay. It also helps when things get, well, ugly. Like that one.
Okay.
Sometimes people look at this and they get confused because now it's not just x squared, it has an x squared and a y squared. And there is no GCF. There's no number in common, there's no letter in common all the way across these three terms. But it has to follow the similar pattern. So you look at the last term, which is 16. I don't care about the y squared, I really am interested in that 16. So it's factors of 16 that subtract up to negative 6. And we'll worry about the y in a second. So what are factors of 16 that subtract up to negative 6? A positive 2 and a negative 8. So I'm going to write it as 2 minus 8. Now, I need that middle term to be negative 6xy. So my 2 and my 8, both of them have to have xy. They have to, otherwise I wouldn't be able to go backwards. So it's a positive 2xy, a negative 8xy. Bring down the first term, bring down the last term.
it's like it's like all our life we were told to walk this way, and now you telling us no, that didn't work. You need to walk this way.
No, I never said walking your way wouldn't work. I'm just saying you won't be able to run after this.
Exactly.
Well, let's put it this way. Your shortcut is crawling. I'm eventually going to teach you how to walk.
So you chose to work with the last two because they had the ones in common. They had the y in common.
No, you always take the last number, the coefficient.
Okay, take the last.
Yeah,
number.
so you're going to say, well, factors of 16 is subtracted to -6. You ignore all the letters.
Okay.
The only time I did this over here, I was really
Because
careful.
they had a common.
Well, yeah, there was common factor. I want to get it out. But if they don't, you just jump to that last term and just start the language of it all.
Okay.
And whether you're going to do the shortcut or not, the language still works because you still have to come up with those two numbers. All right, and then we start grouping. So group the first two. What pulls out?
X,
What's left behind?
X plus 2.
X plus 2,
Y.
Y.
Oh, I forgot my
Yeah, don't forget anything. What can I pull out of the second one?
-8.
I can pull out a -8.
Negative 8, Y.
Don't forget the Y, so kick out -8Y. Left behind?
X
+2.
plus.
X plus 2Y. Now we have something in common, the X plus 2Y. Kick them out. X plus 2Y. After we divide him away from the other two terms, what do we get left behind? X minus 8Y.
It doesn't matter which order.
No. Why? I could have put the 8 first and the 2 second up here. What property allows me to flip them?
Oh, don't say.
I won't.
Community.
Commutative.
Because the community
Commutative of-
shares.
Yeah,
That's
you
how
would flip
I
the order. And if you think about it at the end, what would happen if you flip the 2 at the beginning is the 2 at the end would flip, and that's commutative multiplication. Perfectly safe. That's why I love properties. You don't have to actually show another example. You can just say, oh, it's just commutative. Okay, so that's wonderful for lead coefficient of 1. Those are both considered lead coefficient of 1 because they have this big 1 sitting in front of them. So what happens if we have something that does not have a lead 1? Where would it come from? Well, we're going to multiply two binomials together. And the binomials are going to look like this. AX plus B times CX plus D. Where A and C, not both of them are 1. One of them could be, but the other one has to be something other than 1. And the way I'm going to say that is A times C cannot equal 1. I'll say the absolute value of A times C cannot equal 1. In other words, I don't want both of them to be 1. I just want, and we're talking integers here, not fractions. Integers, no fractions. Be safe. Because you can have fractions that multiply together and give you 1, and there still wouldn't be a lead coefficient. No, that would be a lead coefficient of 1. Whatever. If I multiply this together, what do I get?
ACX squared.
ACX squared.
You get plus
ADX.
BCX.
BCX.
ADX.
BD.
BD.
BD, not BDX, just plain old BD. This one's a lot messier than the other one I showed you. The other one I showed you was x squared plus a plus bx plus a plus bx plus ab. And it was kind of easy to see where things were, well, going. This one, not so nice. Can I combine the middle two terms?
No.
Why not? They have a common factor. Kick out the x, what's left behind? AD plus BC. So, before it was, factors of the last number that add or subtract up to the middle number. Here, if I concentrate on the last number, is that going to give me all the numbers I need for the middle number? No. See, this one only has a B and a D. Is this B plus D? D minus B? It's none of that. The problem is A and C are coming from the first number. So what we need to do is mix all these factors together. And the easiest way to mix the factors of AC and BD is to literally multiply them. So the language is going to change just a little bit. You're going to multiply first, and then you're going to get an answer, and then you read it exactly the same. Factors of this that add up to the middle number. There is a trick buried in there if you can find it. Because one of the factors is coming from the beginning and the other factor is coming from the... So you're mixing factors back to front. And if you can find the factors that way, usually it helps when the numbers get really big. Not so helpful when the numbers are kind of small. All right, let me show you what I mean here.
So is that the answer? What's the
That's as far as you're going to get with it. What this allows you to do is, this is a trinomial. We're going to break it up into 4 terms. And then after that, yes, sir.
Couldn't you have done it also with the other one, the X?
Here?
Yeah.
Yeah, I mean, 1 times 16 is 16.
But I'm saying, you said if you can take something from the first one and then take something from the
Like, the
last.
first one only has a 1 here.
That's only when the leading coefficient is
It's different than 1. Yeah. See, with 1 here, you can do it, but it's not going to change anything about the last number. But if this is 2 or 3, then it's starting to change that.
Can we see one with a number?
Yes. No, I'm going to just let you look at this and figure it out for yourself. Nah, I'll show you one. Example, 6x squared minus 7x minus 3. 6x squared minus 7x minus 3. Now, can you pull out of GCF? No. So your next step is going to be
Take the last.
6 times 3.
Oh.
And you're going to get, that's where you're going to start your language from. You're going to multiply your first number and your last number, get an answer. That takes all your factors and just shoves them together into one number. Then you're going to say, well, what are factors of 18 that subtract up to a negative 7?
2 and 9.
2 and 9. So we're going to separate this into a 2 and a 9. What kind of 2, what kind of 9?
A positive 2, negative 9.
Positive 2, negative 9. What variable do they both need? An x. And I'm going to bring down that negative 3 at the end and the positive 6x squared in the beginning. I haven't done anything different. The pattern I use for the lead coefficient of 1s is carrying over for this one. There is a shortcut for the lead coefficients of 1. There is no shortcut for this one. That's why I'd rather you just do it the long way. That way you never do anything different. All right, GCF of the first 2. It's 2x. Left behind? 3x plus 1, because we pulled out all the factors. What's the GCF of the second 2?
3.
Careful, negative 3.
Negative
Left behind is going to be
3. X minus 1.
negative 9x divided by negative 3. 3x. Negative 3 divided by negative 3 plus 1. Now they have something in common. 3x plus 1. Don't they? This one here. This one here. What's left behind after you divide those away? 2x minus 3. And there is a perfectly fine factor. And that's why I do things the way I do it. I don't do it this way to make the easy ones hard. I do it this way to make the hard ones easier. That's the whole trick of math, making things that are hard a little bit easier. When you can do that, things become nice. Do I have an uglier one? Oh, yeah. Oh, no. We got to build it up. They all have the same technique built into them. Let's see. This is not too bad.
How much did all that cost?
Huh?
How much did all that cost?
You don't want to know.
Did you pay for it?
Heck no.
I was like, did the school pay for it?
Oh my gosh, yes. You think I'd go out and buy one of those? No. Now, if I was an online tutor, I would have bought it because then I could have paid for it over time.
This has a
Over time, golly, that sounds like.
Well, that's all investments. You put money
Yeah.
into something, like your education, just because you think you're going to make more money eventually.
They have a GCF.
Was
They
that your
have they have a
Was
GCF.
that your idea or the school idea?
My idea.
Yeah, I figured school would come
No, I'm weird that way.
with that.
Okay, so you look at this and you say, oh, it has 3 terms, but before you do anything, don't be multiplying 6 times 16 because that won't get you anywhere. They all have a common factor of 2
And Y.
and a y. You kick them out first to make things a little bit nicer. So 2y on the outside, that leaves
8x squared plus 2x minus 3.
Yay! So now I got it down to this. We can ignore the 2y because he's been kicked out of the house. So we worry about what's left inside.
That last
It doesn't have a lead coefficient of 1 because it has that 8 sitting out front. So we need to take the first number and the last number and multiply them together. So 8 times 2, or I'm sorry, 8 times negative, well, don't even worry about the negative. 8 times 3 is 24. This is where you're going to start your language. What are factors of 24? That subtract up to a 2.
6 and a 4.
6 and 4. So we're going to break up the middle number into 6x and 4x. What kind of 6x? What kind of 4x? Positive 6
And then negative 2.
and a negative 4. That'll give us a positive 2x. Bring down the first term and don't make it 2y. Remember, we're ignoring him. Bring down the 8x squared. And bring down the,
Minus 3.
and then group and factor. GCF of the first two.
It is
2x, left behind,
4x
minus,
plus 3.
I'm sorry, plus 3.
plus 3. GCF of the second two.
There is none.
If there is none, you have to pull out at least a 1. In this case, I want to pull out
Negative
negative 1. So pull out a negative 1, left behind,
4x plus 3.
change their signs, 4x plus 3. And when you get to this point, you say, I must have done it right because the two binomials are identical.
Okay, makes sense.
So you kick out 4x plus 3. What's left behind?
2x minus
2x minus 1. And please do not forget
2y.
that 2y that was sitting out in the front.
Almost forgot.
So your final answer is this ugly mess.
Alright, so I just want to make sure I got it.
Okay.
You get the GCF.
If it has it,
If it has it,
kick it out.
kick it out. You bring the GCF down, and that's going to be on the outside,
Uh-huh.
whatever inside.
Uh-huh.
And then you take, if it has a, I don't know what you call it a lead coefficient?
Lead coefficient.
A lead
A
coefficient.
number that has a number in front.
Yeah, a number in front outside of a 1.
Multiply
You
the first.
multiply the first from the last, and then you just
Do your
kind of
process.
pull backward foils that I call it.
Right.
Backward
You,
foil.
backward foil. Backward foil.
Done.
Which is perfectly fine way of saying it. It is backward foil. You're undoing what was done. It's almost an inverse process. Inverse.
We need one more.
I'm not sure if I have one. Oh, I do. I'll let you do this one.
Just to make sure.
I think. Wait a minute. No, that's this one. 8. Oh, this one. 8x squared plus 6x minus 27. This one does not have a GCF. I'll give you that hint. This one does not have a GCF. Maybe I'll help you with this one because watch what happens. 8 times 27.
Is negative 216.
216. Now, the problem with 216 is most people don't know their multiplication facts over 100. Like over here, this one was easy. It was 24. 8 and 3, 6 and 4, 2 and 12. Most people know that. What are factors of 216?
2 and 108.
2 and 1.
2, yeah. And the best way to do this is say, well, 1 and 216 are factors. 2 and 108 are factors. 3 and 72.
72.
4 and 54. You're wondering how I'm doing this without a calculator. 5 and, no, 5 doesn't go into it. 6 and,
9.
what?
What?
216. Not, 216 divided by 6. 36? 7? No, 7 doesn't go into it. 8? 8 goes into it. 8 and 27? Right? Therefore, 9 must go into it. 24. 10? No. 11? No. 12? 12 goes into it. 18. Ooh, wait a minute.
That's it.
That's it, right?
Mhm.
So, if the number gets too big, there's a couple methods you can use. This is one of them, though this one takes a little bit of time. There is another way
You
of
don't
doing
like
it.
that.
But it would be 12 and 18. It would be a positive 18 and a negative 12. Let me show you an alternate way of doing this. Most people won't do it this way. I'm just showing you for those people that can look at it and go, oh, I see. Remember when I multiplied ax plus b times cx plus d, and I said the factors were coming from the front and the back, and they were actually mixing to give you two different numbers. What's a nice factor of 8?
2 and 4.
2 and 4. What's a nice factor of 27?
3 and 9.
And if I mix them front to back, you can have 6 and 36, right? That's right there. Or you can have 18 and 12.
Wait.
Oh.
Because the whole idea is you're mixing factors from the front and the back. So I'm mixing factors front to back pairwise. So the trick is, if you can do this, it's usually the nice factors. You'll find that you can get those two numbers rather quickly. It's a neat trick. Most people don't do it because they get confused with it. So my other suggestion is, if you get confused, just do the whole list. It doesn't take that long, and you will find your two numbers. But be very careful. Keep dividing by numbers one at a time. Don't jump around. Because if you miss one of them and it happened to be the one you're looking for, you'll never find it. All right, so it's going to be 12 and 18. You finish it. I'll give you the numbers. You can finish the problem. Where? Laziness will get you nowhere. Did half the work for you. You just have to do the other half.
Four x plus 9 minus 4 x plus 9, 2x minus 2.
Sounds friendly. Let's see. Gcf of these two.
That's what I thought.
4x. That leaves behind 2x minus 3. Gcf of these two. Positive.
It's 9.
Positive 9. Left behind is going to be 2x minus 3. So you get 2x minus 3 and 4x plus 9. Yay! See, once you get the two numbers, everything else is easy. It's getting the two numbers and using them correctly. All right. So that leaves uglier stuff. Well, actually nicer stuff. Yeah, we got plenty of time.
Remember, we don't get out till after.
I know. I'm being very cautious. Factoring. Special binomials. There's two types. There's perfect square binomials and perfect cube binomials. Let's deal with the perfect square first. If we have a perfect square binomial, it's going to look something like this. This is called the difference of perfect squares. The other one would be, of course, the sum of perfect squares. There's like 3 or 4 different ways of explaining how this factors. One of them is actually geometric. Want to see the geometric one? Most people don't want to see that. So let's do it that style. Is this a trinomial?
No.
Yes. I can make it one.
Yeah.
What's missing? An x, right? But I can't put in 1x because that would change the problem. So what can I put in there that doesn't change the problem? What number can I add to any other number without changing it? That's times 1. You can add 0. So what I'm going to do is I'm going to expand this out to become x squared plus 0x minus 4. Using a couple properties here. 0 times x is 0. 0 minus 4 is minus 4, so you get x squared minus 4. So it doesn't change anything, but it allows me to do the factoring exactly like I have been. What are factors of 4? Let's subtract up to 0.
2 and 2.
2 and negative 2, right? And if we kind of jump ahead, the answer is going to be x plus 2 and x minus 2. There's also another name for those two binomials. What are they called? Conjugates. The middle two terms cancel out, negative 2x and positive 2x. So when you're factoring x squared minus 4, it factors into x plus 2 and x minus 2. If I put one of these on the test, you say thank you, because these are way too easy. How about 81x squared minus 25? Well, they're perfect squares, and the technique actually works this way. X squared turned into x's, 4 turned into 2's. What property am I using? Well, how do you change a 4 into a 2? You can either A, divide by 2, or you could take its square root. So, square root of x squared is x, square root of 4 is 2. Square root of 81x squared.
9x.
So you're going to get 9x in the front of both of the binomials. Guaranteed, without a doubt. Because 9x times 9x is going to give you 81x squared. All right, square root of 25, I gave you the answer. 5 and 5. And just make one plus and the other one minus. Ta-da, done. Okay, so how about x squared plus 9?
Minus 3, x plus 3.
That's a sum.
Problem. There's a problem with the sum. If I expand this out, I get x squared plus 0x plus 9. And when I go for the language, what are factors of 9 that add up to 0?
It's not possible.
It's not possible, because if you add up, they're the same sign. 3 plus 3 is 6. Negative 3 plus negative 3 is negative 6. You'll never ever get 0. This one is considered prime. Be careful with that one. So this really only works on the difference of perfect squares. You can only factor the difference of perfect squares. The sum of perfect squares is prime. Okay, so that's the easy one. Square root everything, plus minus, as long as there's a minus in between them to begin with. The harder one is the perfect cube. For instance, I need you to multiply this out for me. Let's get a new partner. Seconds. Should be able to do it quickly. Distribute, distribute, distribute. Is that your final answer?
No.
Good.
No, not them breaking it down.
Hey. Someone practiced their polynomials. The more you practice with polynomials, go to the P4 section and crank through all those problems. The quicker you are, the better you're going to be at a lot of this stuff.
Is that right?
Yes.
Okay.
Easy to tell if you're right. Something fancy happens. You should have been getting 8x cubed minus 27. 8x cubed minus 27. 2x times 4x squared is 8x cubed. 2x times 6x is 12x squared. 2x times 9 is 18x. I saw a bunch of you just keep adding terms to the right. I highly suggest you don't do that because it makes things a little bit harder. When you get to negative 3 times 4x, put it right under the other x squared term. And that way they're right next to each other, you can see exactly what's happening. And negative 3 times 6x is negative 18x. And negative 3 times positive 9 is negative 27. Add them together and you get 8x cubed minus... Woohoo!
That's
Didn't I teach you how to do that? I'm quite sure I did. Quite sure it's in your notes. All right, so what's cool here is I ended up with a binomial, and the numbers are all perfect cubes. So this would be considered the difference of perfect cubes. And it does factor, but it factors a little different than the difference of perfect squares. Perfect squares is a binomial times a binomial. Perfect cubes is a binomial times a trinomial, and that's the important thing. You have to remember that you're going to get a bi-tri piece out of this. When you factor a cubic, you're going to get a bipart and a tripart. Right. And there's also a pattern built in here. The 8, if I take the cube root of it, is 2. Cube root of x squared, x. Cube root of 27, 3. That gives me the first term. To get to the second term, you have to look a little deeper. To get from 2x to 4x squared, all you're doing is squaring, or multiplying it by itself. To get to 6x, well, that's 2 and 3x times together, and you change the sign. This one was minus, that one is plus. And then 3 going to 9, that's easy, it's just square 2. So the pattern is this. If I have x cubed plus 64. So the first step is, number 1, take the cube root of everything. If you take the cube root of everything, that gives you the binomial piece. So you're going to get x plus 4. The second part you have to remember is a trinomial, and the pattern is square, multiply, square. So you square the first term, so you get x squared here. You take the two terms and you multiply them together. 4 times x is 4x. Change the sign, so this becomes minus 4x. Let's square the last term. It's positive 16. And you're done.
Okay,
Square, multiply, square.
This is square,
Well, cube root everything first.
cube.
You get your first binomial term. You want me to write this down?
Yes.
Please.
1 cube root gives you binomial term of your factoring. 2 square first. 3 multiply 2 terms.
Square first what?
First term. Multiply 2 terms. Change sign. And 4 square second term. The book has a formula, but as formula goes, it says exactly the same thing as what I'm putting up here.
real quick, make up another one.
Oh, these are not hard to figure out.
Well, I just want to.
Ready? 125 x to the 9th plus. Oh, by the way, the sum of perfect squares I couldn't factor, but notice what I did over here. The sum of perfect cubes factors perfectly fine. Kind of like that idea of square roots. You have to be very careful that everything is positive. Well, in this case, it's kind of opposite. You have to make sure that everything in between is minus. All right, 125 x to the 9th plus. Ooh, 1. Why not? 1, for some reason, confuses people. Is 1 a perfect cube?
Yes.
Yeah, 1 times 1 times 1 is 1. Very boring, but it still is. So, to get to the first binomial term, binomial expression, cube root of 125,
5.
cube root of x to the 9th,
3. X to the 3.
cubed, right, divide by 3. And then the cube root of 1, of course, is
Plus
1. To get to the trinomial part, square the first term, multiply the two of them together, change the sign, square the last term. So the first term squared is x to the 6. Multiply the two of them together, and you get 5x cubed.
Do what now? Multiply.
Multiply these two together. 5x cubed times 1. Just take the two terms and multiply them. Get rid of the plus sign, in other words. But change plus into minus, so you're going to get 5x cubed
Plus 1.
plus 1. If you don't trust me, multiply those two together, and you will find that it does equal 125x to the 9th plus 1. The 2 middle terms, the 4 middle terms, if you want to think of it that way, kind of cancel. Kind of cool. Kind of cool.
Can we do one more?
Oh, sure.
Just to make sure.
And then,
Well,
of
how,
course, we're going to have homework on it, so.
Hold on, let me think of one. I need a pencil. Do you have a pencil? Let me write something down. I'm not sure if it'll work. Let's see if it does. This one? Let's try this. This is not friendly.
And then let us go by ourselves.
Oh, no, you don't want to do this one by yourself.
Oh, I thought you were going to give us the easy.
You haven't seen it yet. X to the fifth minus 9x cubed plus 8x squared minus 72. This takes technique. And the reason it takes technique is because there's more to it than just factoring. Well, no, that's not true either. It is pure factoring, a lot of it. So you look at this and I say, well, factor this thing. What comes to mind?
Separating.
Right.
What's that? Is there a GCF?
No.
No.
8 times. No. Yeah. 8 times 9 equals 7.
Maybe 72.
That's great. 8 times 9 equals 72.
Huh?
How many terms are up here?
4, I mean.
4. You can't factor it like a trinomial, so don't even think of that because it has 4 terms.
Can't you
Group them.
parentheses?
That's the, no, don't put
I
parentheses.
mean, not parentheses, but you know,
Little underline
brackets.
thingamajiggies. Group them. Group the first 2 together. Group the second 2 together. What can I pull out of the first 2?
X to the third.
So if I kick out x cubed, what's left behind?
X squared minus 9.
Alright, works perfectly fine for the first 2. What about the second 2?
8.
I can kick out a positive 8, leave behind
X squared minus 9.
x squared minus 9. Yay! So it does factor by grouping because the 2 binomials turned out to be identical. What can I kick out now?
X cubed.
I can kick out
X squared minus 9.
the common term, which is x squared minus 9. What's left behind?
And then the X cubed plus 8.
Am I done?
No.
No.
Heck no. And this is where people get confused. They think that if they go through one process of factoring, they can just leave whatever answer they get. That works great for most of the ones that we've had, but this one actually does a little bit more. Does x squared minus 9 factor?
Yes.
Yeah.
Yes. It factors into
X plus 3, X minus 3.
x plus 3 and x minus 3. It is the difference of perfect squares. Does x cubed plus 8 factor?
Yes.
Well, yeah. Cube root the first term,
X
X.
plus 2.
plus 2, and then you go through your pattern. Square the first term,
X squared
multiply the 2 of them together,
minus 8x. I mean minus 2x.
minus 2x. It's going to be 2 times x and change the sign. So minus 2x. Square the last term,
Plus 4.
and now this is what's considered completely factored.
Wait a minute.
Go on.
Couldn't you,
Well,
X plus 2, when you got, before you got to that last one, we made it a trinomial, how do you know to do?
this is a cube. This is a perfect cube. When you're dealing with a perfect cube, you cube root the pieces. That gives you the first binomial. Cube root of x cubed is x. Cube root of 8 is 2.
Alright.
Remember, this is like 2 separate problems, a perfect square and a perfect cube, and you got to treat them separately. But you got to keep all their answers together.